Okay, let's take a look at the second half of Chapter 1. So I'm starting where it says Section 1.3, and we're looking at different ways to organize categorical data. So why is it important that we organize categorical data, any data for that matter? Raw data can be messy. It's generally hard to make sense of raw data just by looking at the data by itself, and that makes it difficult to see patterns. And remember, our goal is to take that data and organize it so that we can make some kind of analysis with it. So raw data by itself is hard to work with. We usually want to organize it into some sort of way that we can deal with that format. An example, incomplete data, if you take a look at this picture, so this actually comes from our textbook, but which sport based on this image looks like it's the most dangerous? So take a second and just kind of look through these numbers here, and just based on looking at these numbers, which sport would you say is the most dangerous? And I probably, if you're like me, you probably would have said basketball, and I can see why we would say basketball because that's got the most number of injuries according to this table. But are we missing any important information? Is there anything else that might be helpful in determining if we want to answer the question about what's the most dangerous sport? So we're only given the number of injuries, but what are we missing? So one thing, and there's a lot of answers you could say here, but one thing we could be missing is the total number of players in each sport. So all we're given in this chart are the number of injuries, but we don't know how that compares to the sport as a whole. How common are these injuries? The seriousness of these injuries. Are we comparing apples to apples? Are we comparing a broken thumb to a broken collarbone? Those are pretty different. So the seriousness of the injuries may be something that's missing. And you can probably think of other things that might be helpful to make your conclusion. Those are just a couple that I thought of. So let's look at this again, but with a little bit more information. So when comparing groups, one thing you want to be sure you're looking at is the percentages or the rates. Those are usually better for comparisons. As opposed to in this table, we were just looking at the number of injuries. But like I said, we didn't know how many players were in each sport. So now look at the same data again, but with more information. So we've got our sports again. This time we've got the number of injuries in this column here, but we also have the number of participants in each sport. And so along with that, they've given you the calculation for the rate of injury per participant, the percentage of participants injured, and then of course the rate of injury per 1,000 participants. I'm not necessarily sure that all three of those other columns are needed, but now that you've got the rates of injuries or the percentages, whichever column you want to look at, would you still say that basketball is the most dangerous sport? And hopefully you see that football has the highest percentage of injured participants. So notice there are many more basketball players than there are football players. So the rate of injury per participant is highest among the football players. And so one thing to keep in mind is that you always, when you're comparing numbers across groups like that, you always want to look at rates or percentages to make those comparisons. So let's look at section 1.4 as the last part of chapter 1 and looking at causality. So you've probably heard the expression correlation does not necessarily mean causation. And that's a big deal in statistics, and that's something we always have to keep in mind when we're working with different settings. Causality can be understood in terms of two variables. So if we're looking to show causality, for example, does cell phone use cause cancer? If we were looking at a study on that, we would want to specifically focus in on two variables. One is the treatment variable. So we can think of the treatment variable as whether or not a specific treatment is used. And by treatment, I mean that kind of generally. Whether or not we have a specific characteristic could be the treatment variable. Whether or not we use cell phones, that could be the treatment variable. The outcome, or also called the response variable, is whether or not a certain outcome is seen. So what happens if those people used cell phones, for example, did they get cancer? That would be the response we would maybe be looking for. The goal is to determine if the treatment variable actually causes a change in the outcome variable. So some very specific things have to happen in order to say causality and not just say that there's a correlation there. So if we want to know, for example, here's just a quick example. If we want to know whether a test prep book improves test scores, what would we record? So the treatment variable would be whether or not the book was used, right? So if, we'll say this, if the book was used to study for the test. Okay, so like for example, I'm trying to figure out, does this test prep book raise SAT scores, for example? So the treatment would be whether or not the student used the book to study for the test. What would the outcome variable be? So the outcome would be the results of the test scores. So actually looking at those test scores and trying to see if there's some relationship there between using the book and the higher test scores. With that, we would have what's called a treatment group and a control group. So the treatment group is the group that receives the treatment or has the characteristic of interest. So in my test prep book example, the treatment group would be the ones who use the test book, let's say, or the prep book. The control group would be a group that does not receive the treatment or does not have the characteristic of interest. So in my example with the test prep book, the control group would be the group that did not use the test prep book to study for the test. Placebo is another term that comes up once in a while. So you've probably heard the term. In a physical sense, a placebo literally could be used or could be used to indicate a pill, a harmless pill, or a lookalike of some kind, given in place of actual treatment. And I say it's a pill, and I'm using that term kind of loosely. It doesn't necessarily have to be a pill. It could be somebody thinks they're part of a research study and they're getting some sort of treatment in the study, maybe using a new educational method. And maybe they think they're part of the study, but they're really not, or something along those lines. In medical research, it is oftentimes a pill where somebody thinks they're getting a pill that's a medication treatment for some illness or disease. But in other studies, it doesn't have to be a physical pill. It's just something where you think you're getting the treatment, but you're really not. Along with that, we have what's called the placebo effect. So the placebo effect would be where you actually react to a treatment after being told you're receiving the treatment when you, in fact, are not. If you tell somebody you have a headache and they give you, they call it an aspirin, but it turns out to be a Tic Tac, but you think it's an aspirin, and so your headache gets better. That would be called the placebo effect because you think you got the treatment, but you really didn't. All right. Some things that we need to have, though. So the whole purpose of this little section here is to look at when we can say causality. And so very specific things have to happen and occur in a study in order to say causality. So it has to be what's called a controlled experiment. So a controlled experiment involves when researchers assign subjects to a treatment group. It's not by chance or they're already placed in groups. For example, if I were going to run an experiment and I wanted to compare a new teaching method and I wanted to compare my 8 a.m. class to my 9 a.m. class, well, if I already used my 8 a.m. class and they were already in that group and my 9 a.m. class was already in that group and I didn't randomly assign subjects to a control and a treatment group, that would not be a controlled experiment. A controlled experiment is when the researchers in the study are actually putting subjects in a treatment group versus a controlled group. Generally, we want that to be done randomly. We don't want to necessarily have certain people in one group or another because that could sway the results of the study. So randomly assigning subjects to the treatment group is important when you're looking for showing causality. This often uses technology to keep the assignments random and balanced, and to balance out any differences in the groups or to minimize what are called biases, a bias. And we'll talk about that a little bit more later in the course. Another key factor in trying to show causality in research is that the study is blinding. So a blinding study means that the researchers don't know who's in the control group versus the treatment group. They're just carrying out the experiment, but they don't necessarily know who was assigned to a control group and who was assigned to a treatment group. Or I should say that it's done independently, usually by a third party that's involved in the research that way. Double blinding, let me say that, double blinding is even better, and that's when the researchers themselves don't know. That's what I meant to say. The researchers don't know who's considered the control group and who's considered the treatment group. Every so often, if you ever watch that show, Grey's Anatomy, it's kind of a silly show, but they'll do research on that show, and there's been situations where the researchers themselves, the doctors, don't know who's getting the treatment and who's getting the placebos. And so that would be considered a double blinding study. And that adds a little more credibility and can be used to point to causality. Other types of studies that we may discuss from time to time, anecdotal. So an anecdotal study is a story that's based on someone else's experience. If you interview subjects, that's often called qualitative research, and that would be considered an anecdotal study. An observational study is when the subjects are placed into different groups by choice or by someone else. So if they're in different groups by circumstance, I feel like is a better word. So if they're in different groups by circumstance, let me go back to my example of comparing my 8 a.m. class to my 9 a.m. class for a certain teaching method I'm trying to look at the effectiveness of. That would be an observational study because the students are already in those groups by circumstance. I didn't put them there. I didn't randomly assign subjects to one or the other. This is really important that you remember. Anecdotal studies and observational studies can never imply causality. That's really, really key. If we're looking at an observational study, that's nice. That might give us some support or some credibility that there's maybe a correlation, but it never implies causality. So that's a really important point, that we can't use anecdotal or observational studies to indicate causality. To establish a cause and effect scenario, we have to use a controlled experiment. So quick example here, if you notice that there are long lines when you go to the beach, the number of ice cream sales go up. So does this mean that the long lines to the beach caused an increase in ice cream sales? Well, this is kind of a silly example. You can probably think of a lot of reasons why ice cream sales would have been up. There could have been high temperatures, so maybe it was a hot day. That could have caused ice cream sales to go up, but had nothing to do with the long lines at the beach. Maybe there was a sale on the ice cream. Maybe it was discounted that day, and so sales went up for that reason. So this is an example of an observational study. We observed what's happening. Let me write that out. Observational study. We observed what's happening, but we didn't randomly assign somebody to a control and a treatment group. Another thing you want to be familiar with is what is called a confounding variable, and that's what comes up in this little ice cream study here. Confounding variable is a variable that has, has not been accounted for. Let me write the 4 over here. Oops, sorry about that. Let's go back. Try that again here. So it's a variable that has not been accounted for. There we go. But maybe causing a difference in the groups being studied. So in my example here with the ice cream sales, what are some confounding variables? Could have been the high temperatures. That may have played a role on ice cream sales, not necessarily just the lines at the beach. It could have been that school was out. Maybe sales were up because school is out. I know there's an ice cream shop near my store or near where I live, and the lines are always out the door in the summer. And I think it's because that's one guess. School is out, and so people don't mind doing that more often than they would during the school year. So any other variable that's not accounted for in some way in the study would be a confounding variable. So when you're looking for a well-designed controlled experiment and you're trying to establish causality, things to look for: a large sample size, and we'll talk more about sample size and what we mean by large later on in the course. Assignment to treatment and control groups is done randomly. and is controlled by the researcher, or I should say a third-party person. In other words, they're not in groups by circumstance. Placebo is used if possible, and that the study is double-blind. So the researchers do not necessarily know who's in the treatment group and who's in the control group.